Good morning, friends. The last lectures we were discussing about gross weight and the importance of aerofoil in a generic manner. We also discussed about the speeds required for, let's say, ensuring maximum rate of climb and to fly at a minimum power. And we are trying to discuss in a generic manner how the aerofoil will play an important role. We need not debate much on this point regarding the importance of aerofoil, because after all, lift, which has to be equal to weight for a cruise, is given as half rho v square s CL. This is the dynamic pressure, this is the wing area, and this is the CL what we are talking about. Also, we know, as a designer, we should not only think in terms of CL, we should think in terms of CL by CD, because CL will also induce drag, which we know is called induced drag. So when I am selecting an aerofoil, I should not only think in terms of CL, but also try to see what is the CL by CD maximum I get and under what conditions, and under what speed. So if I try to summarize as far as airfoil selection is concerned, loosely I can say I need to know what is the cruise speed I am going to fly the machine. I need to know takeoff and landing distance required, and also stall speed. I'll explain all this term. Then handling qualities, and aerodynamic efficiency. Why cruise speed should be back of our mind in selecting the aerofoil? Because finally, as the designer, I want that should fly with drag minimum. Also, I should know that if the cruise speed is low subsonic, then there is a drag characteristics, which is differently when I try to design an airplane for high subsonic speeds, or a near transonic speed, or near supersonic speed. That is how the airfoil shape is likely to be different. For example, for a supersonic speed, you want the nose part as pointed as possible, provided you can manage it structurally. Right? Takeoff and landing, why this is important? Because you know, takeoff and landing, that speed takeoff or landing roughly is 1.2 times V stall. Okay? And V stall is 2 W by S by rho CL max. If I want V takeoff or V landing to be lower, then I should ensure the V stall to be lower during takeoff and landing. What indirectly means is, for other things remaining constant, CL max should be high. The CL max could be high, could be possible if you select an aerofoil. Instead of this, if you select an aerofoil where CL max is high. So from the beginning you have a aerofoil selected which will have CL max high, but you understand the moment I look for CL max high, I am mentally prepared to give penalty in terms of drag, even the stall angle may reduce. So to overcome that, you will find people use flaps. We'll come to that. So that this is basic aerofoil, and then you put a flap down, that is, if this is a basic aerofoil, I put flap down some degrees, 10, 20, 30 degrees, and ensure that the CL max is enhanced. So that is where, when you are selecting an airfoil, I also keep in mind takeoff and landing distance, because if V takeoff and V landing speeds are less, and for a given thrust to weight ratio, the takeoff and landing distance also will be less, right? Stall speed, you understand. When I am selecting an aerofoil, I would like to know what is the V stall. I will always like V stall to be as low as possible, but it should not be lesser than the amount. It should not be so less that it becomes too sensitive to wind and the environment conditions. But yes, stall speed depends on CL max inversely. So when I select an aerofoil, I try to see CL max to be as high as possible. Handling qualities. Why handling qualities? Because the performance of the airplane near the stall is a very, very important parameter for the pilot to have a smooth handling or better or good handling qualities. So again, in handling qualities, you find somehow the stall angle, this angle plays an important role. So I need to look for an aerofoil which generally has higher stall angle. And of course, aerodynamic efficiency, which we have talked about. I will look for an aerofoil where CL by CD max is what I look for. It should be higher one, maybe 13, 14, 15, even for gliders, it will be much, much higher, right? If this is from the aerofoil side, what I look for in a design, when I translate this aerofoil into wing, right, there is another important parameter which you should clearly understand, which has direct implication. If I draw an aerofoil, this distance, which I call thickness to chord ratio, this also plays an important role. We could see that if T by C is large, then the flow will accelerate here faster than aerofoil having T by C less. But T by C large gives me an advantage. For a given chord, I've got larger volume in the wing where I can store fuel, I can store other components. Right? But the point is, as I increase T by C, the drag may also increase. So I have to be careful. If I increase T by C, the M critical may reduce. If I increase T by C, these are all generic statements. If increase T by C, M critical may reduce. So T by C will play an important role. And as a designer, without thinking of big aerodynamics, you could see if this T by C is large and the flow accelerates faster than decelerates, so there could be a region where there is a high adverse pressure gradient and flow may separate in a manner which you don't like. The flow may not exist as a laminar flow. If you are designing a laminar flow aerofoil, the flow will become turbulent sooner than you are desiring. So T by C also will play an important role. Now you can understand, when I am generating data for different types of aerofoil which are to be used in the database, we used to call NACA aerofoil. Nowadays, of course, you have a customized aerofoil. But if you see, when the data were generated, data will be generated in such a manner that it will give you thickness to chord distribution, the leading edge, radius. It will tell what is the speed for which CL by CD is maximum, what will be its CL max I can achieve. All those parameters will be given as a parameters to select which aerofoil you want. So I will just go back to the NACA aerofoil era and explain you some nomenclature to understand what is the aerofoil and what are its special features, so that we can select aerofoil based on those nomenclature. Before I go for the nomenclature, which is purely mechanical thing, but we as a designer should know how important it is for us to understand the database, why those nomenclature. Before I go to that, let me also explain you. If you recall, most of the drag polar CL and CD of an aerofoil takes this sort of a shape, and we say this is the minimum CD. Now the point is, you'll find latest aerofoil which are being used, their shape not only looks like this, it may be something like this, then goes like this, and there is a bucket. Oh, sorry. There is a bucket like this. This is a bucket formation. Typically, this sort of aerofoil where CL by CD shows a bucket, we call it laminar bucket. The importance is this: if you see during this region, even if there is an increase in CL, there is hardly any increase in CD. But if you see the other type of aerofoil, where it is something like this, and this is CL and this is CD, if there is increase in CL, the CD will go on increasing. Right? Here it is this. So as a designer, I will prefer a laminar bucket type aerofoil, so that even if I am changing CL because of different operational requirement, I do not give too much of drag penalty. But please understand, this is typically a laminar aerofoil, and nomenclature wise you will find there are 6 series aerofoil mostly. But there is an issue with laminar bucket type of aerofoil is that if there is a slight imperfection in the construction, even if you find some insect material, dead material is there, the flow immediately becomes turbulent, right? But there is a trend that mostly people will be using 6 series or derivative of 6 series or customized 6 series aerofoil. So it's called 7 series, 8 series, all those things. The idea would be, what is the nose radius I am looking for? What is the point where I am finding out that the CP, pressure coefficient, is becoming 0? It is not necessary that pressure coefficient is 0 only at T by C maximum location. Because CP is 0, or pressure coefficient 0, is an important parameter, because then I know where from the adverse pressure gradient will start acting, or pressure gradient variation, how it will act, which will be responsible for flow separation. Right? With this background, let us come back to the nomenclature part. I will not talk about all the nomenclatures available, but few one, and it is expected that you read books and really understand why these nomenclatures and how much a designer can take information from those nomenclature. I am adding few more designers' perspective before we go for the nomenclature, especially to get a feel how thickness ratio will implicate in terms of flow separation on an aerofoil in a very generic manner. And I am referring a text from Raymer's book. You can read Raymer's book. So I give a heading, a stall, and I say important role. you will find some aerofoil will show gradual reduction in lift, and some aerofoil will show violent loss of lift and rapid change in pitching moment. For example, if you take Kimber aerofoil wings, this is a Kimber aerofoil wing. If you see this diagram, its CL max will be more, but it will have large CMAC negative. That is, if I just throw it, it's natural tendency to go down like this. Right. So in Raymer's perception, he has explained 3 types of stall. Very wonderful summary of his experience, and I thought it must be shared. One, he talks about fat aerofoil. That is rounded. What is the characteristics? Rounded leading edge. That is, if I draw an aerofoil, this leading edge is rounded. I can put a circle here. And T by C, thickness to chord ratio, is greater than equal to 14%. You may be cursing me. Why suddenly is talking about T by C? What is T by C ratio? Sir has not mentioned anything about how aerofoil looks like, what are their Kimber line, how to select, how to choose, or how to see even a Kimber line. So let me do that for you, which I presume you are all knowing this, because you have done already 2 courses. This is the leading edge and this is the trailing edge. Okay? And this distance is called chord, right? And if I take every section like this, take the middle part, then this will give me the Kimber line, which is the Kimber line. And this is the thickness, or I can say T by C ratio, or thickness non-dimensionalized with chord. So what is Kimber then? If I, for completion, I write and explain you what is Kimber. Kimber, I am in particular to write exactly what is being accepted by everyone, but you could see that through your common sense you can find out what is Kimber. I need not always follow this definition. So is the maximum distance between the mean Kimber line and the chord line This is important. Measured perpendicular to the chord line. This is important. Because here, because the chord line is horizontal here, so we are talking about the maximum distance between the mean Kimber line, this is the mean Kimber line, and the chord line measured perpendicular to the chord line. So that is what is the Kimber. That is, if this is the chord line, this is the Kimber, this is the Kimber, this is the Kimber, this is the Kimber. Okay? It is possible that the chord line is something like this, and mean Kimber line is something like this, and I take the mean position. So that time I will say the Kimber is, I have to draw a perpendicular to the chord line. So that will become the Kimber, right? This should be clear in your mind. Okay, then leading edge radius, which I was talking here, mostly you will find this is 0.0 times C bar, or don't say C bar, chord. 2% of the chord, around that. Okay. So now you know this nomenclature. Now I feel okay to talk about the mechanical thing, that nomenclature. I will start with 4-digit nomenclature. This is NACA, let's say NACA 2412. Okay. What are the information you get from here? That is maximum Kimber is 0.02 C. This is this one. What is this 4 signifies? That location of maximum Kimber is 0.4 C from leading edge. Right, C is the chord. And this 12, that is T by C maximum, is 0.12 C, or T by C is 12%. T by C max is 12%. So once you see a NACA 4-digit nomenclature, immediately from this number, you could easily find out what are the information you are getting. After 4-digit nomenclature, now we are discussing about 5-digit nomenclature. You will find NACA 23012. How to read that? The guideline or the direction is, how to read this is, that 3 by 2 multiplied by first digit will give you design CL in 10th. 3 by 2, first digit is 2, so 3, it will be 0.3. What is the next 2 digit? How do I take information from that? It says next 2 digits divided by 2 gives me the location of maximum Kimber along the chord line from leading edge in 100th of the chord. Right? It's not a big philosophical statement, right? If you just follow it. Let us see if I try to understand this NACA 23012, what other information we get. Let's say 5-digit is NACA 23012. As for the first statement, 3 by 2 into 2, because it is 2 is the first digit, this gives me 3, but in 10th it is telling, so 0.3 is the design CL. Right? Second one is next 2 digit divided by 2. Next 2 digit is 30, so 30 divided by 2 gives me 15, but it says maximum Kimber along chord line from leading edge in 100th of the chord. So 15 divided by 100 is 0.15 C. So it tells me that if I move from the leading edge here and at 0.15 C, the Kimber will be maximum. Okay. And of course, last 2 digit tells me T by C maximum, which is 12%. Right, which is also, we say, 12% T by C max. So this is what are the information we get from a nomenclature, which is 5-digit nomenclature. After 5-digit nomenclature or 5-series nomenclature, we are talking about 6-series nomenclature. The 6 series, when you talk about, you should be mentally prepared that we are now going into a laminar type of aerofoil. Okay. I'll just give you an example. NACA 641, 212 and A equal to 0.6. What does it mean? The 6 is a series designation for the nomenclature, and you should understand that for a 6 series aerofoil has been designed to maximize the region over which the flow is laminar. Advantage: the drag over small region of lift coefficient can be substantially reduced, because laminar will give reduced drag. But I have been telling you the word of caution, the manufacturing becomes a challenge, one is very particular, and maintenance of the surface of the wing is also very, very important. In fact, if I tell cleanliness of the surface, that is also a challenge, and one has to be particular about it, because slight impurities or foreign elements sitting on the wing may turn the flow into a turbulent flow. Right. So that was all about 6. Now the next one is 4. 4 tells you location of minimum pressure in 10th of chord. That is, if this is the wing aerofoil, and as you know, there will be acceleration, so there will be pressure drop, and there will be a point which corresponds to the minimum pressure point, and that is being explained here, that at 0.4 C from the leading edge, you will have a point where the pressure coefficient will be minimum. What is that 1 indicates? 1 indicates that low drag is maintained at a lift coefficient equal to 0.1 above and below the design lift coefficient 0.2. Where from this 0.2 came? This is from here. The next is 2. So 0.2 is the design lift coefficient, from here. And this 1 tells you that 0.1 or above or 0.1 below 0.2, you will have the drag coefficient or the drag lower, right? So we say indicates that low drag is maintained. As I was mentioning, for a 6 series or a laminar type aerofoil, there is a laminar bucket, right? That is being talked about. If I further clarify this, okay, this is your laminar bucket, okay? If this is the design CL, then 0.1 above and 0.1 down will have low drag configuration. Right? So this is also important, because as a designer, you need to know all the time you are not going to fly at design CL. So what are those off conditions, and whether your aerofoil is optimally selected or not. Right? So that helps you in this. T by C is 12, T by C max is 12%, and also A equal to 0.6. This is also additional information you get from a 6 series nomenclature. It tells you 60% of the chord, over 60% of the chord, this is over 60% of the chord, the pressure distribution is uniform. It goes like, it's not that sharply, it's not falling. Okay, so it will be over 60% of the chord, the pressure distribution will be uniform. That is also important when you talk about minimizing drag or flow separation, stall, and all those things will be very clear when I talk about supercritical aerofoil. These are the steps towards defining a supercritical aerofoil as well. You'll see that this is very important. A equal to 0.6, 60% of chord distribution is uniform. I started with Raymer's perception about aerofoil as a designer. I started at some point, then I went back to the nomenclature. I'm again coming back, and please appreciate what a designer should have. All these nomenclatures are fine, theory is fine, but as a designer, how do you perceive things? He characterized the aerofoil as fat aerofoil, thin aerofoil, very thin aerofoil. So for fat aerofoil, what is his message to us is typically aerofoil rounded leading edge and T by C greater than or equal to 14%. And what we will see is such aerofoil near the stall. It is important we are discussing about stall and how an aerofoil should have characteristics near the stall, because that is going to decide the handling qualities, which is very important design parameter. Says for a fat aerofoil, which are rounded leading edge T by C greater than 14%, such aerofoil stalls from the trailing edge. Then turbulent boundary layer. Boundary layer becomes very turbulent as angle of attack increases. And the flow separation starts from trailing edge and moves towards leading edge as alpha is increased. The loss of lift is gradual. This is very important. And pitching moment changes are small. Understand this, the loss of lift is gradual and pitching moment changes is small changes. It starts stalling from the trailing edge. Okay? And boundary layer becomes turbulent as we increase the angle of attack, which has direct implication on the drag part. Right? So if I try to draw this, if this is an aerofoil where T by C is greater than 14%, if I translate those observations, it says stalls from the trailing edge. So separation, so stalls from the trailing edge. As I increase angle of attack, this stalling or the separation moves towards the leading edge. And finally, whole flow separates. And in that process, loss of lift will be gradual and pitching moment changes will be smaller. This is the perception of Raymer when he talks about fat, which are rounded leading edge aerofoil with T by C greater than 14%. If you are a designer, you will find how useful are these observations. Similarly, he has talked about thinner aerofoil. Let me talk about thinner aerofoil. After that fat aerofoil, let us also see the thinner aerofoil as per as Raymer's perception. Typically, the T by C between 6 to 14%, around 9-10% will be okay. We talk about thinner aerofoil. And those are, as a designer's language, we call it moderate thickness. When you say moderate thickness, means 8 to 9%, 10% like that. The moment you are going beyond 12, we are cautioned, it's no more a moderate thickness. What is the beauty of those aerofoil? The flow separates near the nose at a very small angle of attack. Very small angle of attack, flow separates. But at small angle, flow separates but reattaches. But as you increase the angle of attack, there is no reattachment and suddenly the flow stalls or the flow separates. And there is an abrupt change in CL and pitching moment. That's what one designer should be very, very clear if you are working with this sort of aerofoil, depending upon what flight regime you are flying, what angle of attack you are flying. So typically if I represent small angle of attack, there may be separation, but it reattaches. But as angle of attack is increased, there is no reattachment, and suddenly you will find the whole flow will separate. Very abruptly the flow separates. But this happens from leading edge to trailing edge. This is important. The flow separation starts from leading edge to trailing edge. Unlike for fat aerofoil, it was from trailing edge to leading edge. So the lift loss was gradual. But here, it starts from leading edge, so naturally the leading edge portion is the portion where the lift generation is most efficient. If that part stalls, naturally the lift stall will be very, very abrupt. And naturally, there will be abrupt change in lift coefficient and pitching moment coefficient. So that is the story when you are working for a moderate thickness aerofoil, which are nomenclatured as thinner aerofoil. The last one, which I want to share with you, is very thin aerofoil. Right? Very thin aerofoil. Again, it is Raymer's perception. So I am says flow separates from the nose at small angle, at small alpha, and reattaches immediately. This is fine. It says separation bubble stretches towards trailing edge as alpha is increased. So if I try to see the similarity between what we're talking about, thinner and very thin aerofoil, here you will observe loss of lift is smooth, but large changes in pitching moment. That is the difference, very thin, maybe 2, 3%, 4% T by C. You'll find flow separates from nose at small angle of attack and reattaches, same. Separation bubble stretches. So it is something like this. If this is thin, there is a separation bubble. Now, as I increase angle of attack, the separation bubble goes over this, and then further if I increase angle of attack, this whole separation bubble that breaks. The movement is from leading edge to trailing edge. So this is separation bubble stretches toward the trailing edge as alpha is increased, and there is a separation here. Observation is the loss of lift is smooth, but large change in pitching moment. So this is what the perception of or knowledge base shared by Raymer. And as a designer, you need to see this vis-a-vis the aerodynamic characteristics of different aerofoil, right? And you sit with an aerodynamist and talk to him, what does it mean? How do I customize my aerofoil so that this thing doesn't happen or this thing should happen, right? So that is why there is a constant interaction with the aerodynamist when a designer looks for a particular type of performance. For example, if he is designing an airplane or an unmanned aerial vehicle of Heron class, 600-700 kg weight, speed is not high, so it is prone to experience large angle of attack if there is a vertical upward gust. So designer will ask the aerodynamist, can you give me an aerofoil which has a very good stall characteristics? Designer may not be satisfied with whatever aerofoils are available, even customized aerofoil characteristics, the designers may not be happy about it. There is a limit to which an aerofoil shape can be configured, but then designer will not sit idle. That is what I'm telling you, what a designer, how a designer different from a person who is doing analysis. One designer, what it will do, okay, this is the maximum stall angle you are able to give with this aerofoil, so I'll put a split aerofoil here. The split aerofoil, the Heron has used that. So what will happen, if this was not there, this was having a stall angle, let's say 12-13 degrees, the moment you put a split aerofoil, then you could see that air goes from here and comes out like this, and it pushes the stall, so the stall angle increases, right? The important thing is, how do you contour this part so that the air coming should not go like this, it should come and follow the path. That is where the $1 million design, wind tunnel testing, CFD, etc. plays role, right? So whatever I'm trying to give you, I'm sharing few knowledge base of designers, few from analysts who are analytical person, and also try to give you example how you are not an aerodynamist, you are not a structural man, you are a designer, right? And you have to be smart. Just being bright will not make a good designer. A designer has to be sufficiently bright, and more importantly, he should be smart as well. Are you prepared for that or not? We'll learn from these courses, and I can guarantee you that we will become all smarter. Thank you very much.